Non-recursive algorithm analysis. The content of this presentation is referenced from the book Introduction to the Design and Analysis of Algorithm by Anani Levitin. I'm Efina and I will be presenting this topic. The topics of discussion are a brief overview of the summation formulas that will be helpful in deriving the time units of execution of an algorithm, the rules for computing the time complexity of the algorithm, which is the sum rule and the product rule, and few examples for derivation of big O for non-recursive algorithms. Few summation formulas that are helpful in calculating the time units of execution of a given algorithm is given here. The most generalized one is the summation I extends from L to U 1. This represents that the programmed statements are executed for 1 unit of time each and the number of times of execution extends from the lower limit L to the upper limit U. Then the summation formula is U minus L plus 1. Considering program statements that has constant C times of execution units, and if those statements are executed with a minimum of 1 number of times to n number of times, then the summation formula sigma I extends from 1 to nc equals c multiplied by n. The summation formula for a single loop structure is given as sigma I equals 1 to n I, which equals n multiplied by n plus 1 by 2. The summation formula for nested 2 loops is given as sigma I equals 1 to n I square, which equals n multiplied by n plus 1 multiplied by 2n plus 1 by 6. Similarly, for a 3 looping structure, it is given as n squared multiplied by n plus 1 whole squared by 4. The two rules for computing the running time of non-recursive algorithm are the sum rule and the product rule. The sum rule states that if P1 and P2 are program segments that occurs sequentially in a program P, and if the time complexity of P1 is T1 of n equals big O of f of n, and the time complexity of P2 is T2 of n equals big O of g of n, then the time complexity of the program P consisting of the program segments P1 and P2 occurring sequentially is given as T of n equals big O of the maximum of f of n and g of n. So what is the product rule? The product rule states that if P1 and P2 are program segments that occurs nested in a program P, and if the time complexity of P1 is T1 of n equals big O of f of n, and the time complexity of P2 is T2 of n equals big O of g of n, and the time complexity of P is represented as T of n equals big O of f of n multiplied by g of n. As we have discussed the summation formulas and the rules for deriving the time complexity of a given algorithm, let us apply them in few examples. Example 1. Algorithm for finding the value of the largest element in a list of n numbers. The algorithm max element takes input list A with n elements. The algorithm declares a variable maxval which will store the maximum value in the list A of n elements. Initially, maxval is assigned the value of the first element in the list A. Using the for looping structure, we browse across each element in the list and compare it with the maxval value. If the element compared is greater than the maxval value, then maxval takes the value of the element that is compared. At the end of the loop, maxval holds the largest element in the list A, and that value is returned. So, the time complexity of the n-1 iteration in the I for loop is given as sigma I equals 1 to n-1 1, because the statements inside the for loop takes 1 unit of time for execution. Applying the formula, which is u minus L plus 1, we apply this formula to the limits. So it is n minus 1 minus 1 plus 1. So the result is n minus 1. As we have discussed previously in our presentation, when the time units of a given algorithm is n minus 1, then the time complexity of the algorithm can be represented as big O of n. Example 2 checks whether all the elements in a given array of n elements are distinct. The algorithm unique elements takes input array A of n elements. The algorithm consists of nested for loops with the outer for loop with I variable and the inner for loop with j variable. The outer for loop selects the element to be compared with every other element in the array. The inner for loop browses across every other element in the array. The statement if inside the inner for loop compares the element selected by the I for loop with every other element in the array. If a match is found, the algorithm returns a false, indicating that the array does not have unique elements. If the match is not found, the algorithm returns a true, indicating that the elements in the array are unique. Now let us compute the time complexity of this algorithm. The units of time of execution of each statement is as given. 2 units of time for the I for loop statement, 2 units of time for the j for loop statement, and the comparison if statement has 2 units of time and the return with 1 unit of time. The time complexity function for n-1 iteration of the I for loop is given as sigma I varies from 0 to n-1 of the inner J loop. You could note that the I value range from 0 to n minus 1 is the same range represented in the for loop of the algorithm. The time complexity function for the J for loop is derived using the summation formula J equals I plus 1 to n minus 1. The range of J represents the range of J in the algorithm J for loop, which is I plus 1 to n minus 1. The summation is applied to 1 because the statements inside the J for loop takes 1 unit of time for execution. Applying the summation formula, the time complexity function for the J for loop is n minus 1 minus I. Substituting the time complexity function for the J for loop in the time complexity function for the I for loop, the summation is represented as sigma I varies from 0 to n minus 2, n minus 1 minus I. The range of I is taken from the range of the I for loop in the algorithm, which varies from 0 to n minus 2. Simplifying the sigma formula, the time complexity function for the algorithm is obtained as n multiplied by n minus 1 by 2. Applying the principle of big O notation, the worst case time complexity of the algorithm is derived as big O of n squared. Example 3 finds the product of two n cross n matrices A and B. The algorithm matrix multiplication receives input matrix A with dimension n cross n and matrix B with dimension n cross n. The algorithm consists of three nested for loops. The outer for loops with the iterator variable I and j selects the row and column of the resultant product matrix C. The inner for loop with k iterator variable selects the elements in the corresponding A and B input matrices and computes the product. The algorithm returns the product matrix C. Let us derive the time complexity function for the matrix multiplication algorithm. To do that, let us find the time complexity function for n iteration of the outer I for loop. It is represented in sigma notation as sigma I equals 0 to n minus 1 of the inner J for loop. To find the time complexity function of the inner J for loop, we use again the sigma notation as sigma j equals 0 to n minus 1 inner K for loop. The sigma notation for the inner K for loop is derived very similar to the I and the J for loop as sigma K equals 0 to n minus 1 of 1 because the statement inside the K for loop requires constant number of units for execution. Simplifying the sigma notation, we get the time complexity function for the matrix multiplication as n cube. It is represented using asymptotic notation as big O of n cube. Example 4 finds the number of binary digits in the binary representation of a positive decimal integer. The algorithm binary receives a positive decimal integer n as input. The while loop in the algorithm counts the number of binary digits. Hence, each iteration of the algorithm reduces the input n to half. Hence, for a range of n values, the number of iteration of the while loop remains the same. For example, for the value of n ranging from 8 to 15, the number of iteration of the while loop is 3. Hence, the number of binary digits used to represent the decimal values from 8 to 15 is 4. When there is such an algorithm where the number of times the while loop is executed is the same for some range of input values, then the time complexity of such an algorithm is denoted by log. Here it is represented as big O of log n. To conclude, I would like to summarize the topics of discussion in this presentation. We discussed briefly the overview of summation formulas that are helpful to derive the time complexity of a given algorithm. We discussed the rules for computing the time complexity of the algorithm, which are the sum rule and the product rule. We discussed 4 examples for deriving the big O notation for non-recursive algorithms using the summation formula and the rules for computing the time complexity of the algorithm. Thank you.